Our next speaker is Professor Bala Iyer, who will tell us about gravitational physics at RRI from 1975 to 2022, themes and highlights. It's a great pleasure to have him here today. Professor Bala Iyer has contributed enormously to work on gravitational waves and has given us a very important legacy of work that RRI should be extremely proud of. Bala joined RRI in 1980 and was with us until 2014. He's currently a Simons Visiting Professor at ICTS and co-PI of the LIGO India Scientific Collaboration. Bala has worked extensively on calculations of gravitational waves from inspiraling binaries and neutron stars. This is analytic work. And whatever we've seen on the news about gravitational waves, he has contributed so significantly to that. These are the templates, these are the gravitational wave templates, using which we can deduce what that astrophysical phenomenon has been, whether it's neutron star mergers or black hole black hole mergers, and in this way opened up new windows into our universe. So let me give you a brief bio about Bala. He completed his BSc, MSc, and PhD PhD was 1980 from Bombay University, and joined the Raman Research Institute and was here from 1980 onwards to 2014. He's a fellow of the APS and International Society on General Relativity and Gravitation. He's been chair of the Indigo Consortium from its inception in 2009 and was PI of Indigo participation in the LIGO Scientific Collaboration during 2014 to 19. He was a member of the core team for LIGO India mega project proposal. He's been a visiting scientist in France, UK, Germany, and US, and he's been involved in the Research Education Advancement Program for BSc students at the Bangalore Planetarium for over 2 decades, and has also been involved in public outreach on GR and gravitational waves.
So let me begin by thanking Tarun for this invitation to share with you the evolution of gravitational physics at RRI, but I changed the title to indicate this one. So let me just get on to my brief. So according to my understanding, research in gravitation in RRI began in the mid-70s when Haridas Vishweshwara and D. M. Chitire, representing broadly tests of GR, black holes and their perturbations, and GR and astrophysical phenomena were hired. My talk highlights the work done in gravitation by the following, and in the periods indicated: Haridas, Vishu, Sanjeev, myself, Sam, Madhavan, Sumati, and Suparna. It would be uneven in details and not exhaustive due to my own limitations. Broadly, the themes are the following: spin tests of GR and the Feynman derivation of the quadrupole formula, exact solutions, trajectories in the presence of electromagnetic fields, the use of Hertz potential to study perturbations, the notion of ultra-compact objects in GR, black holes in higher dimensions and their quasi-normal modes, Frenet-Serre formalism for black holes, the work on gravitational waves in which me and my group were involved, the approaches to quantum gravity, 3 different streams which have been pursued at this institute, the work on rotation in GR by Sam, and finally the work on atom interferometry and redshift. In the rest of my talk, I will basically attempt to briefly elaborate on each of these themes. So let's begin at the beginning. So in this paper, which was the New Binary Pulsar and Observation of Gravitational Spin Precession, the authors gave a detailed model of the pulse width and the polarization sweep as a means of observing the geodetic precession in general relativity. It was followed by another paper by Haridas, where he tried to ask the question, if you look at intrinsic quantum spins, will they behave differently from the orbital angular momentum when you have gravitational fields? And no, from here, can't you hear me? Let's get closer. Is it better? Yeah. And the next one is a paper which was far ahead of its time, where the authors tried to derive the classical energy loss formula for gravitational radiation by the Feynman graph method. This has become a very big industry currently, and therefore you can see that this was far ahead of these authors were far ahead of their time. The next theme relates to problems in classical GR with possible astrophysical implications. So the kind of questions you ask here is, if you look at the perturbations of black holes in general relativity, they carry signatures of the effective potential around them, and you could look for those signatures by examining, for example, neutrinos from gravitational collapse, or asking whether ultra-compact objects would exist in general relativity. The next question you can ask, for example, is, can you characterize black holes in higher dimensions in a covariant and geometric manner using the Frenet-Serre formalism? Can one discern differences between black hole solutions in general relativity and other theories of gravity by looking at their quasi-normal mode emissions or the properties of their horizons? Can you use the Frenet-Serre formalism to study gyroscopic precession? How does magnetic field affect accretion? Because you can look at the effect of the magnetic field on the effective potential and hence say what happens in the case of the accretion. I will next move to the broad theme of gravitational waves, in which I and my students were seriously involved. I began working on gravitational waves during my sabbatical with Thibaut Damour during 89 and 90. LIGO was funded in the early 90s, and coalescing compact binaries of neutron stars and black holes were its prototypical sources. The efforts to construct accurate waveforms for mass filtering started, but it was soon realized in Kip Thorne's group that far higher order of waveforms would be needed to approximate gravitational waves when they are in their final stages of inspiral and merger. It's not enough to use what was available for the binary pulsar work. And therefore, Kip really had an international meeting in 1994 to brainstorm this issue and to highlight the urgency to address this particular problem. At this meeting, Luc Blanchet, Sanjeev Dhurandhar, and I were among the participants. And in that meeting itself, Luc expressed the view that the MPM-PN formalism could be extended to do this, and very soon demonstrated what we call the 2PN generation of gravitational waves. Immediately afterwards, I was visiting Thibaut at IHES, and this led to a collaboration between the three of us. The setting up of what is called today as the BDI formalism, where you go from the source movements to the radiative moments via an intermediary canonical movements. The availability of the 2PN equation of motion from the binary pulsar work facilitated the computation of the 2PN phasing by our method, and this calculation was also independently done by Will and Weisman using another related formalism called Dyer. And then at the end of the calculation, we compared our results and we agreed, and therefore we are confident that what we had calculated by this method, by these methods, were really, sort of reliable. You needed to, deal with Einstein's nonlinearity, so you needed to deal with the cubic nonlinearities of Einstein's equation, and this is really the technical hamper, things which have hampered the calculation for some time. Now, when you look at the new binary neutron stars, you catch the LIGO catches them in their inspiral phase, but when you look at the binary black holes, you catch them when they are about to sort of merge. And therefore, you needed more accuracy, you needed the next order of approximation. But then, when we tried to use the earlier self-field regularization, which was done by Hadamard methods, we realized that there was a problem with that regularization procedure, and it led to undetermined coefficients in the equation of motion and in the energy flux. So there was a lot of, difficulty for many years until, for example, it was realized that if you use a gauge invariant regularization called dimensional regularization, then the problem would be overcome. So in two different approaches to the equation of motion, the new regularization was used, and then we also sort of realized that different coordinates require different levels of not only regularization, but you also need renormalization in some particular cases. So all these things were sort of resolved, and finally we could use the same method to calculate the 3 pm calculation of the wave flux, and therefore finally you could do what was, you could get the results for what was needed for the black hole case also. Once the phasing was obtained, the students in my group, in collaboration with my colleagues in France, basically calculated the 3pn gravitational wave polarization, and therefore this really led the stage for knowing everything about the inspiral phase of the coalescing binary system. But then, the approximation which we use breaks down at some particular point, and then you use mathematical techniques like resummation methods like Pardee approximation to extend the domain of convergence of your approximation. This became a little more formalized in what is called the effective one-body approach to gravitational wave calculations, and then in this particular case, new version of the EOB templates was given by myself and Damoor and Nagar in 2008. This was important that we use this because today all the calculations of the EOB really use this as the framework to do the EOB computations. Even though there are theoretical calculations of the results, they are fairly sort of involved. So therefore, in a series of papers with Damoor and Satyaprakash, we provided a digested version of the analytical results for gravity wave applications. And this really was useful for doing detection and parameter estimation work in gravitational wave data analysis. In this series of papers, we basically developed the tools to deal quantitatively with template construction and to understand the template issues which are there in characterizing these templates. This immediately led us to using these analytical results to do parameter estimation and then use it to test the Einstein's theory, and then to use the advantages of using the full waveform rather than what is called as the restricted waveform. So this was a body of work in which Satyaprakash and a lot of students in my group were basically involved. So in a sense, I would summarize by sort of saying that all this particular work really was the foundation of the Indian presence in the test of gravity activity, which happens today in the LIGO-Virgo collaboration. The MPM-PN formalism is currently the most successful since it can deal with all aspects of the problem. The conservative equation of motion, how to calculate the radiation field at infinity, how to calculate the nonlinear effects related to tails, and over the last 25 years, it has developed into a consistent algorithmic approach for analytical gravitational wave computations, and as a part of the textbook by Maggiore, for example. I would also say that the MPM-PN and numerical relativity can be thought of as the scaffolds which underlie the impressive arch of the EOB and phenom template families which are used for detection, parameter estimation, and tests of gravity. The PN work, the test of gravity work, and the work on quasi-normal modes by Vishu are quoted in all the gravity wave discovery papers, and it's gratifying that the PN work is referred to also in Kipthon's Nobel lecture. There is a particular theme which is followed by my group from 1995 to 2014, and this is going beyond what is called as the quasi-circular inspiral to quasi-eccentric inspiral. So the group around me worked in extending the famous Peterson-Matthews results to eccentric binaries to fairly high orders. And if you really want to deal with eccentric binaries, in addition to the energy, you really have to worry about the angular momentum which is emitted by the system, the conserved angular momentum of the particular system, and this really is part of the thesis of the students who work basically with me. Once you have the fluxes, you can calculate the secular evolution of the orbital elements under very high radiation reaction, and also improve on it by calculating the post-adiabatic correction to the secular evolution. So this particular body of work essentially forms the thesis of the students who began with me, Gopakumar, to the last one, which is Chandrakant Mishra. The reason this is important is because the next interesting class of sources which we may see would be eccentric binaries. We know that they should be there, so I would classify them as the known unknowns of gravitational wave astronomy. Starting 2009, my interest really, turned away from source modeling to something else where, I got sort of dragged into it. It's like, a consortium was formed and somebody had to chair that particular consortium, and I landed up with that particular job. And then we basically explored a collaboration with Australia. And on the Indian side, we tried to bring together scientists from various Indian institutions who had the potential, who were interested in and had the potential to contribute to gravity wave experiments. These were scientists at RRCAT, TIFR, IPR, and IUCAA. And then it was an interesting phase because all the students from IUCAA and RRI who had gone abroad to gravity wave groups had come back and started their own groups. So they were ready to participate in the LIGO scientific collaboration via the Indigo group. So that really happened at the same time. And then globally what happened was that after the success of initial LIGO and Virgo, it was realized that better science required a global network. This led to the idea of the LIGO Australia kind of proposal, and when that didn't turn up, it ended up with the LIGO India proposal in 2011. As you know, the in-principle approval of the LIGO India mega project happened 1 week after the announcement of the gravity wave discovery in February 2016. And currently, the LIGO India scientific collaboration has about 100 members from about 15 institutions in India. So you can see that in the area of gravitational waves, it began with a very simple theoretical thing, which began with my sabbatical with Thibaut Damour, but essentially took away the next 20 years of my life. I then move on to the next theme, and there is a theme of quantum gravity, which Sam basically has touched on. Just to say what is the problem of quantum gravity, the construction of a full quantum mechanical description of gravitational radiation remains an outstanding open problem in fundamental theoretical physics, and the quantum gravity effects are expected to be dominant in extreme situations like the Big Bang and deep inside the black holes. If you look at Einstein's GR, it identifies gravitation with the geometry of space-time, and we can expect that quantum gravity will revolutionize the notion of space-time, and the paradigm shift which will happen could probably exceed whatever has happened because of quantum mechanics. So now let's go to the approaches to quantum gravity which have been sort of pursued. The first one I'll talk about is loop quantum gravity, which goes back to Ashtekar. So this generalizes the familiar techniques which we have in quantum mechanics and quantum field theory and applies them to gravitation. But technically and conceptually, this is very intricate, basically because in quantum field theory, you have quantum fields which evolve in a fixed space-time. The background is fixed. Here, the geometry of space-time itself is dynamical, and therefore you need a generalization which does not rely on the notion of a fixed background space-time. So this is a technical complication which Sam basically has said nobody has an idea of what the final solution is. So we can only keep trying different approaches, and that is what really happens. So I begin with the first body of work which happened starting 1987 by Sam, which used the Ashtaker's variable. So Sam basically worked on Ashtaker formalism on topics like the covariant Lagrangian approach to Ashtaker variables. So Sam produced the Lagrangian which completely reproduced Ashtaker's theory, and the remarkable feature was that this Lagrangian was sort of polynomial in its variables. He then used this particular gauge theory gravity analogy to calculate gravitational instants using the Ashtaker's variables. There's also work by him on Bianchi cosmologies, where it was sort of realized that if you really look at a model, the number of degrees of freedom in these models is not uniquely determined only by the isometric group, but depends also on the choice of the topology. And therefore, if you're trying to do quantum theory in these kind of cosmologies, the theory is sort of sensitive to the choice you make for the topology. And there are other papers by Sam in this particular area. 10 minutes. Yeah. In 1997, Madhavan joined RRI, and he really has been working on the Hamiltonian approach to this particular problem. So again, to recapitulate, what is loop quantum gravity? Loop quantum gravity is an attempt at canonical quantization of the Hamiltonian formalism, where one splits space-time into space and time, reformulates this as Einstein's equations, as Hamilton's equations on phase space, and seeks to replace Poisson brackets between functions by commutators between their operator correspondence. There is a fine understanding of how to describe quantum geometry, that is the loop quantum gravity kinematics. But the open problem is how to describe the loop quantum gravity dynamics. And a deeper understanding of the classical aspects of this particular problem is a prerequisite to really do the quantum aspects. And this is exactly what Madhavan has focused on. Madhavan has worked on classical and quantum aspects of gravity within this particular approach. I'll just list 2 or 3 things which he has worked on. The primary contributions have been to the development of a satisfactory quantum dynamics within this particular approach. And finally, there has been a breakthrough which he has recently come up with, which may play an important role in the quantum construction by using the Hamiltonian approach. A second contribution has been to understand this very amazing thing, that how do 3D graviton excitations, how are they related to what happens in loop quantum gravity, where you have one-dimensional graphical excitations. This question, answer to this particular question would be important to understand the semi-classical behavior of loop quantum gravity. And again, a very important problem which insight has come from this particular work, where you basically have kind of evidence that ultimately a resolution of the information problem will be in the point that you really have to resolve the singularity. So a solution to the singularity resolution will give you something which will tell you something about the information loss problem also. So I would just sort of summarize by saying that all this body of work has not only consequences for the construction of quantum dynamics for loop quantum gravity, it also connects to diverse areas like the double copy developments of perturbative gravity and conceptual problems, puzzles which are pertain to the relation of general relativity to its self-dual sector. It also leads to interesting mathematical physics connected with the infinite dimensional graded algebras. Sumati joined RRI in 2003 and since then has been working on the causal set approach to quantum gravity. The basic question is, what do you quantize? Do you quantize the metric, the connection? What causal set theory basically says is that you sort of quantize the causal structure or the causality relation between the space-time events. And therefore, in this particular approach, the continuum space-time is replaced by an ensemble of locally finite, partially ordered sets, and this partial ordering corresponds to the causality relation and the volume element to the cardinality of this particular set. So again, I will not go into the details of it, but I'll just basically flash that there are various breakthroughs which have really happened, which has allowed one to move forward in this particular program also. So I will not really go. Sumati, in her own lecture in the coming week, will probably talk more in details about it. I just basically summarize what the final conclusion would be, that all these results basically are, the research themes which have been pursued here have made substantial contribution to the field of causal set theory. They have pioneered the use of high performance computing for simulations for both the kinematics and dynamics of causal set theory. They have been the driving force behind advances in research in causal set theory dynamics, aimed at answering questions which other approaches have been tackling. It has advanced our understanding of possible quantum dynamics of causal sets, quantum field theory on causal sets, and revealed connections with other approaches to quantum gravity. I just want to conclude by work by Sam and Supurna finally, because they are really interesting. In a paper, The Gravitational Analog of the Monopole, In this particular paper, it was presented a simple and physically motivated discussion of gravitational monopoles using what Sam mentioned, the exact analogy between rotation in stationary space-time and magnetic fields. This work rediscovered the nut solution and presented a general argument to show that closed time-like loops are inevitable if gravitational monopoles exist. The next thing I want to talk about is the lens-theory effect in the Marx principle. There was a claim by Rindler that the lens-theory effect is anti-Marxian. In this nice paper, Sam and Bondi basically showed that this interpretation depends on how you formulate the Marx principle. And if you had a different formulation, then it would have an opposite conclusion. The last thing I just want to mention is a very interesting paper by Supurna and Sam, because there was a claim by Mueller and his collaborators who tried to reinterpret old experiments on atom interferometers and say that it was a sensitive test of gravitational redshift at the Compton frequency. This was contested by the Meudon group of Wolf and others. It was a complicated analysis, but Supurna and Sam essentially looked at the notion of an exact clock in general relativity, analyzed the atom interferometry experiment, and showed that they did not test the redshift at Compton's frequency. So this was one of the two papers which is quoted in trying to show that the claim was sort of basically wrong. And this was followed by another interesting paper in 2015, which asked the question, is there a fundamental limit to the stability of clocks? It pointed out that if you take into account gravity and quantum mechanics, such a fundamental limit does exist, and this limit comes if you put together the uncertainty principle, the gravitational redshift, and the relativistic time dilation effect. If you apply it to a hydrogen maser clock, the number is a part in 10 raised to 22. So I would again point out that these four papers reveal a remarkable conceptual insight which brings together fundamental principles of the theory and their observational implications. So, to conclude, the major themes in gravitational physics at RRI during this period related to tests of GR, black holes and compact objects, gravitational waves, loop quantum gravity, and causal set theory. Research in these areas was timely, long haul, and well aligned with the global frontiers in the subject. It created a body of work that was impactful, unique, and relevant for progress in the field. The group at RRI carved their niche and are recognized for it. I would just end with an acknowledgement. Thanks to Tarun for this invitation to do this summary, Madhavan and Sumati for inputs on their research contributions, and of course the RRI library for the imprint resource. Sumati sorry for rushing over your part, but we will do a better job than I did.